Okay, so at the end of the last video, I gave you this question. Um, and like we are calculating the probability that there is only one cancellation. And to do this, the most fundamental approach to this question is to make a probability distribution table like this, listing all the possible outcomes. Let's do this. This is 8 possible outcomes. So there are 3 reservations, and each reservation has 2 possible outcomes. So in total, there are 2 by 2 by 2 possible outcomes. So, like say, 0, 0, 0 is non-cancelled, and 1, 1, 1 means all the reservations are cancelled. So 1, 0, 0, 0, 1, 0, 0, 0, 1 are the 3 cases, 3 outcomes that our event includes. So we are interested in only one reservation is cancelled. That means only 1, 1 and 2 zeros like in the realization. So these 3 out of 8 possible outcomes are included in the event we are interested. And therefore, what we are calculating can be written this way. Probability that there is only one cancellation equals A cancels, B doesn't, C doesn't. Or plus the case where A doesn't, B cancels, but C doesn't. B cancels, but A and C don't cancel. Or another case, the third case is A and B don't cancel, but C cancels. So it's like specifying who is canceling. When I say only one cancellation, then you have to think about all the possible cases, like who cancels, and then calculate probability for each case. And then apply the special multiplication rule here. Cancellation probability is 10%. Non-cancellation is 90%. 0.1, 0.9, 0.9, they are multiplied. For the first case, right, when A cancels, it's like this. And when B cancels, A and C have 90% realization, and B has 10%. Cancellation has 10%, non-cancellations have 90%. And finally, C cancels with 10%, but A and B do not cancel with 90% each. So again, actually the 3 cases have the same probability. Each of the 3 cases has the same probability, so we do not need to calculate each of them. Just multiply 3. If you understand there are 3 possible cases, you don't need to consider each of them, but just multiply 3 after calculating a single probability. And the single probability consists of 0.1 and 0.9 twice. That means in any case, there is one cancellation, which is 10%, and 2 non-cancellations, which is 90% squared. 90% is multiplied twice. So each case should have probability 0.1, 1 cancellation, and 2 failures, 90%, 90%. So this is the answer. This is how we calculate this probability. And the answer is, I did not calculate that here. Anyhow, if you use a calculator, it's easy to derive the answer. I forgot to write that down. Anyhow, the point here is we see some pattern. We understood how it works. So when you have 2 reservations, it goes like this. And when you have 3 reservations, it goes like this. So the number multiplied here is the number of cases included in this event, right? So when you have 2 reservations, you have to think about A cancels or B cancels. So there are 2 cases. But when you have 3 reservations, It could be A or B or C. So you have to consider three cases. So the first number captures the number of outcomes in that event, number of possible cases in this event. And the second part, this is the probability of a single case. And it's how it's, or like, so let's think about this first. So these numbers capture this, and this part is the probability of a single outcome. So we are going to study this part first because the first part is much more complicated. You may think it's easier, but actually it's more complicated. It's coming up later. So there is also a pattern in single outcome probability. So as I said, the pattern is 0.1, which is the success probability, is multiplied as many times as the number of cancellations. And 0.9 replaces whenever non-cancellation happens. So it is multiplied as many times as non-cancellations. So simply, success is replaced by success probability, and then failure is replaced by failure probability, and then multiplied. So, and it doesn't care whether it is A or B or C, all the same. So as a result, in general, we can write it this way. So in general, there are n number of reservations, and say P is the probability of success. In our example, cancellation. And if you're interested in probability that the number of success equals to lowercase y, then single outcome can be calculated, the probability of single outcome can be calculated this way. So already I specified that the number of success equals to lowercase y. Lowercase y, so success happens y times. So probability P, success probability, must have happened y times. And what's remaining is the failure. So even if I'm only writing the number of success, it also includes the other side information. So the failure happened n minus y times. So out of n times, y was success, then the other n minus y must be failure. And that happens n minus y times. A failure probability 1 minus p happens n minus y times. So you have to multiply them. So you try n number of trials. So in total, you are going to multiply n probabilities. Success replaced by success probabilities, failure replaced by failure probabilities. So in the end, you can extract this formula from that observation, from that pattern. Success probability to the exponent of number of success, and failure probability to the exponent of the number of failures. Right? It's pretty intuitive, right? So these two parts, success and failure, must be counted. What is often missing is the failure part, because everything is stated in terms of success. Like I said, the number of success equals to y. So many people forget about the failure. Failure must happen, right? So this part is usually quite often missing. So please don't be confused. Follow this step by step. And don't forget to include failure probability, even if it's not stated explicitly here. Okay? So I am going to generalize it even more. Now for reservations. Now then, for reservations, I will consider the case that the number of cancellations is 2. You have 2 cancellations, but you don't know who canceled and who not. So then try this and see what's going on. pause the video, and this practice, it's a practice, and you may be wrong, but don't worry, it's natural. Like, even if you're wrong, Okay, I assume you have done. We are going to calculate. By the way, when there are four reservations, it's 2 by 2 by 2 by 2. So 16 possible outcomes. But let me use our patterns. The patterns we found first. Single outcome, in this case, can be calculated this way. There are two cancellations. So cancellation probability multiplied twice. And what's hidden is two non-cancellations. So 90% must be multiplied twice. So, excuse me, we get this probability for a single case. So single case has 0.81%. And what remains is simply to count how many different combinations, right? When two reservations are canceled, you can think about like A, B, A, C, like B, C, like that. So there are different pairs you can think of. How can we do that? Brute force. List all the possible cases and see those cases are what we are interested in. So I wrote down all 16 cases, even though it's a little bit inefficient, but safe way to understand what's going on. And there are 6 possible outcomes. That's strange, right? So you have to multiply 6 to this probability. And the answer is 4.86%. Right? So what is surprising here is, I think the principle is pretty clear. You calculate the single outcome probability, which is not that difficult. It is okay. And then what remains is just to multiply the number of possible cases. But where, like, as you see, there are 6 cases. Well, where is the number 6 coming from? So there is like 4 reservations and 2 cancellations. So you may think it would be 2 or 4 or 8, something like that. But actually not. Actually, you had to multiply 6. That's the most annoying part of this distribution model, which I'm going to explain in the next video. That's called the combination rule. Okay, I will stop the video here, and we'll go to a more difficult theory in the next one. Thank you for watching. See you in the next one.